You may remember the galaxy dataset, which we used before in the context of density estimation. This dataset is contained in the package mass, which comes standard with R, and contains the velocities of 82 galaxies that come from 6 well-separated conic sections of the corona borealis region of the sky. When we fitted this model before, both in the case of using EM algorithms and in the case of using MCMC algorithms, we selected the number of components k to be exactly equal to 6. And that selection came from the fact that, well, we knew that the data was collected from 6 well-separated conic sections, so it made sense in that context to use that number of components. Now, what we want to do today in this example is to use the BIC, the Bayesian information criteria, to verify that that choice is actually supported by the data that we have at hand. So you may already be quite familiar with some pieces of this code. In particular, we're going to reuse the code that we had presented before for fitting the model using an EM algorithm. So first of all, we're going to load the data. That's what we do with this piece of the code. And you can see that we also set the seed of the random number generator, and we do that so that we can get consistent results from one run of the model to the next. So next, we're going to compute the BIC for different values of k. And in particular, we're going to compute the BIC for every value of k from 2 to 20 in this case. So that's what this kk max represents. So we're going to construct a vector that contains the calculated values of the BIC. The next thing that we do is to construct a couple of objects that are going to contain the model parameters fitted for each value of k, so for each number of components in the mixture. And then we're going to embed our EM algorithm into a for loop that, as I said before, goes from a model with 2 components to a model with kk max, which is, in this case, 20 components. And for each value of k, it's going to fit the model using the same EL algorithm that we had discussed before. And once we fit the EM algorithm, that's what this section of the code does. So it just runs the old EM algorithm until convergence. So once it does it for one value of k, we're going to store the values of the weights, the means, and the sigma that correspond to the MLEs for that dimension. And then we're going to compute the BIC using this formula here. And so the formula for the BIC has 2 parts. This part has to do with the likelihood function for the data, which has the standard form. And then the second piece is the calculation of the penalty associated with that model. And if you remember from our discussion before, the penalty is always the number of parameters in the model multiplied by the logarithm of the number of observations. And the number of parameters in the model, if you have k components, it's going to be k minus 1 independent weights. Remember that the weights add up to 1, so they are not quite k, they are k minus 1. Then you have one sigma, because you assume that the kernels are the same for all the components or have the same variance for all the components. So you have a single sigma. And then you have one mean per component, so you have kk means. So that's where the value of the penalty comes from. And you could just write, instead of this saying, you could write 2 times k. But I wanted to kind of break it into pieces so that it was clear where the number was coming from. So let's do that. Let's run the for loop. It takes a second to run because it needs to go for different values of k. So it has finished. So now that we have the different values of k, one of the things that we can do is just plot the value of the BIC as a function of the number of components. That's what this piece of code does. And you can see some of the features that we had discussed in the previous lecture about what happens with the BIC. So you can see that for small values of k, so for values around 2, 3, the BIC is relatively large. Then as you start adding components to the mixture, BIC decreases. And we can see that actually the optimal, so the minimum value of the BIC, does coincide with k equal to 6, which is great. That means that this confirms what we had expected. And then as you add more components to the mixture, because now you have more complexity, but you are not necessarily explaining the data better, the value of the BIC starts to increase. You can see that this is not a strictly monotone. You have kind of some local modes in a couple of places, but you can overall see that the global minimum is clearly located at k equal to 6. Okay, so I want to provide a little bit of additional intuition for this. If you remember, at some point we discussed that the value of sigma is related in some sense with the number, or there is a trade-off between the value of sigma and the number of components in the mixture. In particular, as you use more components, those tend to be more localized, and therefore the value of sigma becomes smaller. That is in some sense the intuition that we get by comparing kernel density estimation with mixture models. So let's see how that works out here. Indeed, when you only have two components in the mixture, the value of sigma tends to be relatively large. And then again, it's not exactly monotone, but we do clearly see a decreasing trend that as you take a larger number of components in the mixture, the optimal value of the variance of those components tends to be smaller and smaller, which confirms our old intuition. Okay, so some more intuition on this. So let's look at the kernel the density estimators that come out of all these mixture models for different dimensions. And what I'm going to do is I'm going to plot the optimal value of 6 components in the mixture and compare that density estimator with the density estimators that you get for other dimension sizes that are close to 6 but are not exactly that. So this is a little function that computes the density estimator. Now I'm just going to compute that for anywhere between 4 and 9 components in the mixture. And the first plot that I'm going to do is I'm going to try to explore kind of the left-hand side of this graph. So I'm going to try to see how the optimal estimator here looks like compared to smaller values of k. So let's generate that plot. You can see here, so the blue line corresponds to taking 4 components. And you can see that what's basically happening is that you're smoothing out these two modes and just taking something that is unimodal here. And you're kind of also over-smoothing a little bit these bumps on the sides. So as you move to 5 and as you move to 6, you start to pick the bimodality of the distribution with 5, and with 6 the bimodality is very, very clear, and you also pick kind of more clearly a couple of the other bumps in the data. So you can see, so the take-home message here is that as you increase from, say, 3, 4, 5, all the way to 6, you are actually, your density estimators change quite a bit, and you are tending to fit the data better. So that's why the BIC decreases, because you are increasing the complexity, but you are increasing or improving the fit much more than you increase in complexity. Now let's look at what happens when I plot 6, 7, and 8. So you can see that the case of the black line that corresponds to 6 and the red line that corresponds to 7, they basically overlap. So even though there is a difference in the number of components, for practical purposes you get the same density estimator in both cases. Now, when you go to 8, that is the blue line, you do see there is a little bit of a change, but most of the key features kind of stay the same in the graph. So in this case, you are increasing the complexity of the model without really reaping any benefit in terms of how well you're fitting the data. And so that's why the BIC, again, tends to increase. So now it's the penalty term that tends to dominate, and the trade-off is not enough to compensate for additional complexity. So this neatly illustrates some of the ideas that we had discussed in the lecture before of how the BAC trades off a good fit to the data with the complexity of the model that you're trying to fit.